Hello, today's lesson is 3.1 on uniform circular motion. So everything we've studied so far has been objects moving in a straight line, but now we're going to talk about objects that are moving in a circle. So this is called uniform circular motion or constant circular movement. That's what we're talking here. Just like uniform motion meant constant velocity before, that's what we're talking about here, but just in a circle. So here's a few examples. A hammer throw, a bucket of water on a string, fair rides that send you in a circle really fast. All of those are examples of uniform circular motion. We're taking a look here at the bucket of water on a string. As long as speed stays the same, we can say the object has uniform circular motion. So again, uniform motion, constant speed. If we look at the velocity at different points, we'll see that the magnitude of velocity stays the same because it's uniform motion, but direction changes. Okay, so what we know is that if we were to let go of this string that's holding the bucket at any point when we're whipping it around in a circle, what's going to happen is that object is going to fly off at what we call a tangent. Okay, so you can kind of try this if you whip your keys around on your lanyard and you let go. They don't keep going in a circle, they go off at a tangent to the circle. So tangent just means it touches the circle at one point, this line. And really, if I looked here, I would be making a 90-degree angle with the vector of the bucket flying off and the radius of the circle right there, or the length of the string holding the bucket in the circle. All right, so instantaneous velocity at any given point in time is perpendicular to the radius, like we just saw with that 90-degree angle. And another way of saying this is tangent to the circle. So this would be the instantaneous velocity. We call this, since it's in a circle on our formula sheet, velocity in a circle. So if the magnitude remains constant, then we don't have any acceleration. Again, uniform motion, no acceleration. So we can use good old V equals D over T from Science 10. However, we have to change what these represent because distance and time, when you're talking about something moving in a circle, is going to be different terminology. So we actually change time to be a capital T, and it really does represent time, but when you're going around a circle, it's the time it takes to complete one revolution. We call this the period. We study this a lot in Math 30, and we'll study it again when we do waves in the last unit. Now, what would you imagine the distance that this bucket goes around the circle is? Well, the distance around a circle is simply the circumference of the circle. So we replace distance with 2 pi r. If we put these into our V equals D over T formula, then we get the average velocity for circular motion to be 2 pi r over t, t being period and r being the radius. Now this is found in the circular motion section of your formula sheet. So right under kinematics, unit 1, dynamics, unit 2, we're now in unit 3, circular motion. You can see it's the first formula there. Here's an example. If the water bucket has a period of 1.5 seconds and the string is 1.25 meters long, what is the magnitude of the bucket's velocity? Why are we asking magnitude? Because direction is always tangent to the circle, and therefore it's always changing when the bucket goes around the circle. Here we go. We're given period, which is a capital T, as 1.5 seconds. So in 1.5 seconds, the bucket goes around the circle once. The length of the string, so keep in mind that you would be holding this string in the middle of the circle. The length of the string is the radius of the circle. And remember, the units are all your standard units for physics. The period needs to be in seconds, the radius needs to be in meters. And then what we can find is we can find the centripetal velocity, or the velocity in a circle, using that formula from the formula sheet. Okay, subbing in. Now, never write pi as 3.14. It is not 3.14. Pi is an irrational number that goes on forever. It never ends. So it's not 3.14. It has an infinite number of decimal points. You have a button on your calculator that will do all of the decimal points of pi, and you need to be using that, not 3.14. If we use 3.14, a rounding at the end is often going to be off because we're using a rounded value to start with. So 2 pi times the radius divided by the period. You can see here that the units, when I put them into my equation, give me exactly what I would expect the units for velocity to be, meters per second. I pop this in my calculator, and I'm going to do 2 sig digs because of the period, and I get 5.2 meters per second. Let's try another one. A superplane is flying at a height of 10,000 meters above sea level in a circular path around the planet. Assume it can hold enough fuel to do this in one trip. If the velocity of the superplane is 885 kilometers per hour, how long does it take the superplane to go around the world? So this one takes a little bit of work. First of all, we're looking for how long it takes to go around the world, to go around that whole circle. So we're looking for period in this question. They give us the velocity as 885 kilometers per hour, but I'd like you to do the 3.6 trick, and I'd like you to make that meters per second. So go ahead, kilometers to meters, you're getting smaller. So divide that by 3.6. And we can just leave it with 3 decimal places. Which is about 246 meters per second. And then the radius takes a little bit of figuring out. They tell us that we're 10,000 meters above sea level. But remember, if we've got Earth and then we're 10,000 meters above sea level, that's not the radius. The radius goes to the center of the Earth and then adds the 10,000. So we need the radius of Earth plus the 10,000, and that's going to give us the radius of this circular path that this plane is taking. So I'm going to go to my formula sheet, and I'm going to go to the back page where it gives me, some of these constant values. Like the radius of Earth right here near the bottom, 6.37 times 10 to the 6 meters. Okay, and I know that I need to add the 10,000 meters that the question is telling me. That's giving me a radius of 6.38 times 10 to the 6 meters. All right, we're ready to rearrange our formula now. Our formula is pretty easy to rearrange for period. We want to get t by itself. This is just one fraction equal to V. It's pretty easy to rearrange. Remember that we can simply switch these locations and put T by itself and V on the bottom like that. So let's go ahead. 2 pi, radius was 6.38 times 10 to the 6. And velocity, even though I'm writing 246, I'm going to actually recalculate it, bring it back up to my calculator screen, and use all the decimals. So try plugging this one in. All right, so I am getting 163,065 seconds, which does not take into account sig digs yet, but we're going to fix that right away. I'm going to take this and make it something that's a little more reasonable. I'm going to do dimensional analysis with this number because I don't really know how long that is. When you tell me 163,000 seconds, I have no clue how long that is, but it might make more sense if it's in hours or maybe even days. We'll see. Let's do the first change here by understanding that there are 60 seconds in 1 minute. I put the 60 seconds on the bottom so that the units would cancel. And I'm going to do one more. I'm going to say 60 minutes in 1 hour so that the minutes cancel. And let's see what this ends up being. I'm going to take the number on my calculator screen and I'm going to divide by 60 times 60 in brackets. And I am getting about 45.3. That should be the proper sig digs here. And the units that we have left after our dimensional analysis are hours. All right. Let's look at the next formula. Now that we've done velocity, we can talk about acceleration around a circle. So acceleration is going to be velocity squared divided by the radius. This is centripetal acceleration, and it's always directed towards the center of the circle. So one key to point out is this word centripetal. I'm going to show you in a second the difference between centripetal and centrifugal with an F. And the direction is important. Direction always towards the center of the circle. This is a little bit confusing because if you think about those fair rides, it feels like you're being pushed out of the circle. And certainly if you kind of let go of the bucket or your lanyard of keys, something will fly out of the circle. But the acceleration is what's keeping the object in a circle, and it is actually pointed towards the center. That's a little counterintuitive when you think about it. Here's the explanation of the difference between centrifugal force and centripetal. So one of these is used to explain something in the physics world, and one of them is actually a made-up force that people use incorrectly all the time in everyday English, and it can be kind of confusing to keep them straight. So I've put forces up here in quotations because one of them's a force, but the other one is actually not a force. So they're easily confused because they kind of sound the same, but one of them has an F in it, and that F stands for fake. Centrifugal or centrifugal force, depending on where you're from and how you pronounce it. If you listen to things from the UK, they usually say centrifugal force, but we usually say centrifugal force. If you hear that F sound, that's fake. That's the English language and everyday people not understanding the difference between centrifugal and centripetal force. So centrifugal force is fake. It's that feeling that you have of being pushed out of the circle when you're on, say, a merry-go-round. It's the tendency of an object following a curved path to fly away from the center of curvature. It's also more correctly thought of as the lack of centripetal force. So the direction of this would be along the radius of the circle from the center of the object. Imagine you're just sitting on a merry-go-round or one of those rides at the fair, and it's the feeling that you would feel. It's this feeling of being pushed out of the circle. If you're, hanging on to that merry-go-round for dear life and you let go, it's you flying out of the circle. That's what people think. There must be a force pushing me out of the merry-go-round when I let go. But it's actually the lack of a force keeping you in the circle. That's why you're flying out of the merry-go-round. An example, mud flying off of a tire, children pushed out on a roundabout, which is a merry-go-round. The formula for this, it's not really a formula for this. It is the formula for centripetal force, which is a real force. But lots of times people will use this formula incorrectly and think they're calculating centrifugal force. It was defined by Christian Huygens in 1659. And is it a real force? No. It is the inertia of motion, the tendency of an object in a circle to keep wanting to do what it's doing. Okay, so another way that we can think about this, it's a fake force. You can also call it a fictitious force. Or if you start doing some reading on the internet, you'll also come across the term a pseudo force. All of these just meaning fake force. Centrifugal force is not real. It's what people feel, but the physics of what actually is occurring in terms of a force is centripetal force. So the one with the P is the real force. It's the force that keeps an object moving with uniform speed along a circular path. It's the force that keeps things in a circle. Along the radius of the circle towards the center. So acceleration, remember, was directed towards the center of the circle. Newton's second law says force equals mass times acceleration. Still applies here. So the force, which is also a vector, is also directed towards the center of the circle. So here's your circle, here's your center, here's your acceleration, and also your centripetal force. They're both pointing towards the center. An example of this is a satellite orbiting a planet. Anything staying in a circle, your keys on your lanyard, a bucket of water on a string, people in a fair ride that's going in a circle, anything like that. We'll get to this formula in a couple slides. I'll explain how it works. Defined by Sir Isaac Newton in 1684. So again, Newton's laws still apply to centripetal force. And yes, this is the force that keeps objects from flying out. It's kind of confusing because it's not what you're feeling. You aren't feeling like you're being sucked towards the center of a circle when you're on a merry-go-round. You feel like you're being pushed out to the end. But it's that force, that centripetal force, that's keeping you going in a circle. And if we lose that force, you're going to do the opposite and fly out of the circle. A car takes a curve of radius 15 meters at 45 kilometers per hour. What's the car's acceleration? So this is a good example. Most people drive or at least ride in vehicles. If you have anything dangling from your rear view mirror, you'll be able to see centrifugal force, so the fake force, in action. When you go around a curve, say you're, coming off the highway and you're going around one of the loop-de-loops, what is the thing hanging from your rear view mirror doing? Is it going towards the center of the circle or away from it? Next time you drive in your car, you can take a look and see what it's doing. You can also think of this as how do you feel? If you're going around a circle in a car really fast, are you being pushed to the outer part of the car that's going around the circle, or are you being sucked towards the middle of the circle? You are feeling this fake centrifugal force. And the thing dangling from your rearview mirror is showing this. It's leaning against the direction of the circle. So it's pointing out of the circle. But really, the force that's keeping you from flying off the road is that the centripetal force is pointing towards the center of the circle. So let's take a look at this one. We have radius. We have kilometers per hour, which is a speed. I'm going to go ahead and divide by 3.6 to make that a number that I can use. I'm getting 12.5 meters per second. And we want centripetal acceleration. Pretty simple formula. It's got absolute value bars, which means we just ignore any kind of sign, positive or negative, because it's always towards the center of the circle. So what kind of sign do you give that anyways? So really we're just finding magnitude. Here's my 12.5 meters per second squared divided by the radius, 15 meters. And I'm getting a centripetal acceleration to be 10 meters per second squared. And to put a direction on this, towards the center of the circle. All right, we've done velocity, we've done acceleration. Next thing to take a look at would be force. Remember Newton's second law, F equals ma. It still applies here, but if we would like to do centripetal force, we have to use centripetal acceleration. If I simply take that and replace it by the equation we just used for centripetal acceleration, I get the centripetal force to be mv squared over r. It's just rearranging of Newton's second law. Or not rearranging, but it's just a substitution of centripetal acceleration into F equals ma. Another one that we're going to use over here comes up when we start talking about satellites in the next lesson. The centripetal force can be friction, tension, gravity, whatever. We're used to setting up our F net equations from unit 2. That's just talking about what are all the forces acting in this question. When you have a question that's going in a circle and you want to set up your F net equation, it looks a little bit different in this unit. I want you to ask yourself this question. What force is keeping the object that you're talking about in a circle? So when you're setting this up, it's not going to say F net. It's going to say centripetal force. That's our F net in this unit. It can be provided by, say, the force of tension in, let's say, a lanyard. If you have your keys on a lanyard, and you're swinging them around, what force is keeping them in a circle? Well, it's the tension in your lanyard that's keeping the keys from flying out of the circle. That's what's supplying the centripetal force. Another example, cars on a road that's curving. So cars going in a circle on a road. What is the force that's keeping your car on the road going in a circle? Well, it's a circle, so centripetal force is provided by the friction on the road. Any of you that have gone in a circle when it's really icy will understand that if you don't have a lot of friction on the road and you're trying to keep your car going in a circle, it's not going to stay that way. Next one that we possibly have is a satellite orbiting. What would keep a satellite or a moon or a planet orbiting a center star or a planet or some other thing? What is the force that keeps these things in orbit? It's gravity. So the centripetal force of a moon orbiting a planet is provided by the gravity of that planet. So this is how you set up to do the math in this unit. You decide what it is that's keeping the object in the circle. Is it tension in a string? Is it friction between tires and the road? Is it gravity created by a planet acting on a moon? These are the main three that we're going to study in this unit. I'm going to add here a couple things that you can do for this section. Yes, I need you to read page 242 to 256, but I also need you to do a few examples. So on page 251, I want you to do the example in the textbook plus the practice problems. And I think there's 2 of them. I need you to do the same thing on page 255. And finally, I need you to do the same thing on 256, example and practice problems. There are answers given, so check your answer. And if you're not getting the right answer, don't hesitate to send me an email. I can write up a solution and send a picture to you.